That's supposed to be 3D, right?
But it's really, yeah, that's 3D.
Yeah, so if you look at it visually, it's 4S, 3D, 4P.
Right.
Yeah.
That's not what you. He was writing it for us for PhD.
This is the way I drew it in class. Many times.
But why is 4P before 3D?
Why is 4P before? Why is 4P after 3D, or why is 3D before 4P?
Well, if you're reading it left to right, 4P is.
No, you don't read it left to right. You read it bottom to top. Yeah.
Okay, but why is it?
All the reasons are the same.
Why are the 2S and the 2P different energies? The reason they're different energies is because of the shape of the probability distribution. The shape of the probability distribution means that one of these sets is what we call more penetrating, less shielded from nuclear charge. That type of stuff's covered in Chem 1A. I don't really want to spend much time talking about it, other than what you need to do is you need to memorize this the correct way and then figure out why later. This is the pattern. You memorize the pattern first, and then you figure out what's going on with the pattern. What's going on with the pattern is kind of complicated. And the reason is the 4S gets pulled down in energy because it's more penetrating. The 3D gets more shielded, what we call shielded, and so it's less, it sees less of the nucleus. So all these orbitals want to see as much of the nucleus as possible. And so it depends on the shape. They have quite a bit different shapes to them. And so this is the reason why. But
that one you don't have to worry about why. You just have to memorize the pattern first, and then later on figure out the why. Okay, but we got to make sure we memorize the correct pattern. And so can everybody draw this exactly like this? If you can draw it exactly like this, then you're going to be okay. If you can't, then work on it. Just look at the supplement. It's page 6 of the supplement. Just up to the 4th shell, that's all. You don't have to draw it all the way up to the 7th or 8th shell.
Number 21, the sample test, based on this diagram, how many orbitals we would have in the 4th shell. So it's going to be 1, 2, 3, 4. Just 4.
Okay, number 21, how many orbitals are in the 4th shell?
how many orbitals are in the 4th shell? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals. Each orbital has 2 electrons. And so it takes 18 electrons to fill the 4th shell. There's a pattern in those numbers too. There's something called the 18 electron rule, which I haven't talked about at all. But there's some additional patterns to that that we can
based on that shell. Okay.
And then do all the orbitals, can we talk about their shape? Because on the quantum mechanics diagram, it seems like it's a perfect sphere. Like in the 3D plane, it gives a perfect sphere in which the area there is big, compared to the Lewis diagram, which is actually a circle. So, like for number 6, the p orbitals have a spherical shape.
P orbitals don't have a spherical shape.
So different orbitals have different shapes.
Yeah. Yeah. I asked you to know 2 shapes, the s orbital and the p orbital. Which one was the dumbbell? Which one was the sphere ball? P is the dumbbell and S is the ball. D is cloverleaf, but I didn't ask you to memorize a cloverleaf. Also, you know, this is not the only thing I want. I also want the NLM, you know,
tell me the NLMs.
Which one?
For all of them. Can you tell me the NLM?
Yeah.
This was part of the quiz, but anyway, just keep that in mind.
And the NLM is
The NLM is on page 5.
of the quantum.
Yeah, quantum. You'll see it there. You can correlate it with that.
Because that's over like n minus 1 is L, and M is 2L plus 1.
No, that's a number of M's. And just read. It goes through. It's just three and a third pages worth of reading on the quantum. It won't take you long. There's rules there. It goes from minus L to plus L, like integers going through 0. That's what M is. Okay, what was that question? 21, you said?
Yeah, you said 9 orbitals.
All right. Let me restart this computer. I think I can. Can you read out the question?
The fourth shell of a multi-electron atom contains 9 orbitals.
Okay. True or false?
No, it was multiple choice.
So it would be 9.
So
The answer was 9.
Yeah.
No, answer is 9. Okay. All right. What else?
19.
19. Okay. Can you read out the question for me?
Orbitals are the solutions to the I cannot.
Schrodinger equation?
Yeah.
Orbitals are the solutions? What do you say? Yes? Yes? Yes is correct.
I thought the Schrodinger theory was...
What is the Schrodinger equation? I gave that quiz, the take-home quiz, a while back ago. Do you guys remember that one? You weren't here for that one, but do you guys remember that one? What was the, draw the orbital energy level diagram for nickel? Do you remember that? Does that ring a bell? And chromium or copper, I forgot which
Because those are
one.
the 2 exceptions.
Nickel's not an exception, but chromium's an exception. Only 2 people have turned it in, but. I'm sorry? You don't have it? You can get it from, just get the questions. I wrote it on the board. I wrote the questions on the board. I don't know if he missed class that day or he left early, but it was on the board. Yeah, you could turn it in if you still have it. I'm not going to deduct anything. But you just get the question. You could turn it in later. I'm not going to deduct anything. But just if you guys miss class, this is just from the standpoint of being a student myself. If you miss class, you're still responsible for the stuff you miss. So you got to ask other students, or ask the instructor or do something to make sure that you get the material, because you aren't automatically exempt from that. And so and then it's not like, oh, okay, it's somebody else's responsibility to make sure you have the stuff that you missed. And so if you did miss that quiz, you can still do it. Just turn it in.
Can we do 34 and 39?
Yeah, actually the computer's down, so can you just read out the question?
Yeah, 34 is how many resonance structures does carbonate ion have?
Which ion?
Carbonate?
Carbonate ion? Well, what is the Lewis structure for carbonate?
C is in the middle. And then you're going to have 3
Well, the first step is we got to make sure we have the correct Lewis structure. How do we know we have the correct Lewis structure? 1, we have to have the octet rule satisfied if possible, and 2, formal charges need to be minimized. And so in order to get because I see people draw lots of resonance forms for incorrect Lewis structures, especially for bicarbonate. So this is why I did bicarbonate as the example. That one's notorious. Even for Chem 1A students, they still screw bicarbonate up all the time. But carbonate, does somebody have the Lewis structure for carbonate? What did you guys get? Or does somebody want to write it down? I'm curious what people are doing, because I can write it on the board, but I'm not sure if it's the same as what you're thinking. So. You have it, Shima? Or does somebody else have it? Carbonate? You have it? Can you write it on the board? Let's just see. It doesn't matter if it's wrong. At least we'll catch it now rather than later. It's better. We can catch it. Yeah, CO3 2 minus. You need the bars of his charge.
Bless you.
Okay. Okay. Well, it's good. We want to catch it because before we can answer this question, we got to make sure we have the best Lewis structure possible. And so when we analyze this Lewis structure, we want to first check octet. Actually, before we check the octet, let me tell you the major errors here. Major errors: incorrect electron count. And so let's just make sure we got the right number of electrons. So carbon is 4 electrons, and then we have 3 oxygens. Each is 6, so that's 18, and then a -2 charge, which would be 2 more electrons. So we should have 24 electrons altogether. And so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So the number of electrons is good. Then we look at the next thing, and that is the octet. You look at the octet next. Is the octet rule, does it look like everything has an octet? Carbon is missing an octet. These oxygens are good, except carbon is not. Carbon is only has 2, 4, 6 total electrons around it, and so it's just too shy of an octet. And so, what can we do to make carbon have an octet?
Double bond.
Double bond, yeah. Which one should you pick?
It could be 3.
Yeah, any of the 3. Since we can have any of the 3, we can form a double bond here, here, or here. That means it has 3 resonance forms. So.
That makes sense.
What are they? We also got to look at the formal charge. But we're always going to have formal charge in an ion. How do I show resonance forms? All right, what are the formal charges? Tell me what the formal charges are.
Carbon is 0, oxygen.
Carbon 0, oxygen.
1, 2, 3, 0. Double bond is 0. That one is -1, -1.
Yeah, okay, -1 and -1. Same thing, just these changed here.
Wait, you
What?
how you calculate the charges?
The formal charge? How did you calculate it?
Valence electron minus the electrons that atom contributes.
Yeah, there's a formula for formal charge. The formal charge is equal to the valence electrons minus
The electrons that atom contributes.
the electrons that the atom contributes, or the number of electrons the atom has. The number of electrons the atom has is the lone pair electrons times 2. So lone pair times 2, because both lone pairs belong to it, and then plus the bonding pair times 1.
So
This is the formula for it.
Formal charge is when you do the 50, right? And you split that bond into 1.
Yeah. This is the equation in books. There's other equations in books. The other equations in books is the valence electrons minus
the number of lone pair electrons divided by 2, oh actually no, number of lone pair electrons, sorry, not divided by 2, plus the number of bonding pair electrons divided by 2. This is a mathematical equation that you'll find for formal charge. However, I gave an alternate way of determining formal charge, and the formal charge is when we have 100%, we make an assumption. We assume 100% covalent bonding and then split the electrons. That's what we did.
Professor, can we do number?
But I'm sorry?
Can we do number 11?
Do number 11? Okay, let me just finish this one here. What do I draw between the two resonance forms?
Slash arrows.
An arrow? What does the arrow look like?
Double-headed arrow.
That's a double-headed arrow. So. And then we need this one. So there are a lot of different ways of doing formal charges. You'll see a lot of different equations. If you just want an equation, just use one of these equations here. But what it means is we're making an assumption. Okay, what was the other question?
Number 11.
Number 11? I think this is working. Look at that.
That's right. I got 29.
You got 29? What did other people get on this? 29? It could be, you're right.
29.5, something like
29?
maybe I did it wrong.
I could have done it wrong too. Maybe it's 29.5, which would be closer to 30. You got it?
Yeah.
All right, well, you could do this really quick. Let me just check the answer. So we have 23 grams of PCl3. The molar mass of PCl3, phosphorus is 30.97. 3 chlorines, each chlorine is 35.45. So what does that come out to here? Three times 35.45 plus 30.97. 137.32. Is that what you got?
Yeah.
All right, then what is the percent yield?
84.
Okay, we want PCl5. And so it looks like it's a 1-to-1 mole ratio. So 1 mole of PCl5 for every 1 mole of PCl3. Then let's get the molar mass of PCl5. So phosphorus 39.7, 5 chlorines. 5 times 35.45.
So what is it? On the first one, shouldn't that be mole of PCl3 for every 137.22 grams specific?
This first conversion factor shouldn't it?
Yeah, you have PL5. What do you have on top? What is the numerator say?
A mole of PCl3.
Okay, that's a.
Yeah. It's supposed to be PCl3.
It's not fun. $208.22. Is that what you got?
Yeah.
So 208.22 grams of PCl5. This is pure PCl5 per mole. PCl5. Well, and then we're losing some of it. How much are we going to lose? We're going to lose about 15.2%. So we're only going to recover 84.8%. So how should I write that here? 84.8% yield. 84.8
over 100 grams.
over 100. The unit should be 84.8 what?
Grams.
Grams of what?
Grams of
PCl5 per 100 grams of what? PCl5. Now we have to label these because 84.8 is not the same as 100. So what should I call the top?
Actual.
Yeah, this is going to be the actual yield, and the bottom will be the theoretical yield. And stoichiometry calculates the theoretical yield. And so let's see what we got here. If this happens on a test, you know, obviously you want to double check your calculation. But if you double check your calculation and you double check the setup looks right, and you're still getting an answer that's not on the not one of the choices, then you could always write it in.
29.57.
Okay. 84.8 divided by 100. Yeah. You're right, 29.57 grams of PCl5. And so this was my mistake here. One of the choices should have been 30 grams, but it wasn't. And so in this particular one, after you double check it and you see, hey, setup's right and everything looks right, then maybe I made a mistake, you know. And so this is correct. I made the mistake on number 11. All right, other questions? Uh-huh.
Can you do 41?
41. For the reaction, magnesium solid plus 2 HCl yields magnesium chloride and hydrogen gas. What is the theoretical yield of hydrogen when 12 grams of magnesium is allowed to react with 71 grams, 50.0% by mass HCl? How much excess reaction would be? So in this one, I wouldn't do the comparison of moles method. I mean, I guess you could. I would just do the smaller amount method. And so for the smaller amount method, we just did this yesterday. What's step 1? You got step 1 is calculate the amount of grams of what? Or just calculate the amount. It doesn't have to be grams because I might ask you something else. I might ask you volume. It's not always grams.
The mass.
And so what you want to do is you want to calculate the, I called it starts with a Y. Yield. We calculate the yield. The yield could be in grams, it can be in liters, it can be in it can be in any unit. That's why we call it the yield rather than restricting it to grams because we just did gas stoichiometry. And so I might ask you, calculate the liters of hydrogen gas produced. But in this case, I didn't specify, did I? What is the theoretical yield? Well, if we didn't specify, we'll just do it in grams. It would be easiest. You could technically leave it in moles, and some people did leave it in moles. But moles is too abstract. I'd rather have it in something we can measure easily. For number 41. And so how many people got 41?
I got
What do you get as your limiting reagent?
limiting reagent
mean, limiting reagent would be either magnesium or the hydrochloric acid. What was the hydrochloric as the limiting reagent? Then that makes it tough. If hydrochloric acid is the limiting reagent, then this is a level harder. Let's find out. Because I don't remember what I did. Oops. So 41 for the reaction. Let's see. So what do we want to do? The yield from what? Step 1, we calculate the yield from
magnesium.
Yeah, okay, so we'll go 12 grams of magnesium. Whenever we're given more than one reagent, it's always going to be limiting reagent type problem. So we'll go 12 grams of magnesium. What's the molar mass of magnesium?
24.31.
24.31.
Yeah.
What's the mole ratio?
1 to 1.
And so last semester, a lot of people left it here because, you know, which one gave the smaller amount of moles? But for moles, we can branch off. We can go to liters if we know the molar volume. We can go to grams if we know the molar mass. Probably go to grams. Because to do the molar volume, we would need to know the pressure and the temperature of the gas too, which wasn't given. The pressure is usually just 1 atmosphere, and the temperature is usually 25. But we'll just do it this way. And so, what's the molar mass of hydrogen?
2.02.
2.02. 2.02 only gives us 3 sig figs. And so in this case, I wanted you to use this. We have 2 choices for hydrogen. 101 is when it's in compound. As the element, we're going to use 1008. That will give us 4 sig figs. And so I'm going to use 2.016 grams of H2 per mole of H2. And so we'll calculate the yield of hydrogen from 12 grams of magnesium.
Should be around
And 12 divided by 24.31 times 2.016. 0.995. So 1. Okay, then we calculate the yield of hydrogen from what?
Professor, why is it 3 sig figs?
Oh, 2 sig figs, sorry. 0.995.
The smallest is 12, so it should be 2 sig figs.
Oh yeah, this 5 is not significant, but I don't want to round it. I'll round it later. So then we calculate the yield from 71 grams of HCl solution. The solution is a mixture, homogeneous mixture.
Does the 51% have anything to do with the calculation?
Yeah, the 50% does. Where do I put it?
After it.
Yeah, this is not 71 grams of pure HCl. This is 71 grams of mixture.
So it's 35.5 grams of
Yeah, right. But what we do is we'll just do a dimensional analysis. We'll just say that there is, this is easier than just calculating in your head, just line it up. 50% means 50.0 grams of what per 100 grams of what? This is by mass. This is 50.0 grams of pure HCl per 100 grams of HCl solution. So this tells us how many grams of pure HCl we have, and it would be, you're right, 35. Okay, then what's the molar mass of HCl?
36.46.
36.46. HCl mole. That's what I've got as well. Then what's the mole ratio?
1 to 2.
Yeah. 1 mole of H2 for every 2 moles of HCl. And then the mass is 2.016 grams of H2 per mole. $71 times 50 divided by 100 divided by 3646 divided by 2 times 2.016. 0.98. 1. So what is the theoretical yield? Theoretical yield is a smaller amount. Whether they call it a smaller amount method. What's the limiting reagent? Limiting reagent would be the excess. How much excess remains? 0.01 grams. Shima, did you calculate? How many
Yeah.
grams did you get?
I got 11 milligrams.
11 grams?
No, milligrams.
Anybody else? So we have 0.01. Anybody got the excess reagent remaining? This is why, you know, this is why I did yesterday's calculation the way I did it. I did it because this is your basic limiting reagent calculation, and you should have this mastered, you know, for this class. You know, and the way you get it mastered is repetition. You just do, there are a whole bunch of homework problems, limiting reagent problems. You do them all the same way. If you do comparison of moles, that's fine. You can do it that way. But you need to have this mastered. You're guaranteed to have this problem on the test. You're going to have a limiting reagent problem on the test. It might have some additional twists, or it might be more basic, I don't know. But you'll definitely have them. And so the last step is excess. We had to do a step 4 yesterday. They were asking about something else. And so yesterday was, that's what makes an advanced problem advanced. You know, an advanced problem is advanced because you have to do one extra step or one pre-step or something like this. If you look at all the advanced problems in our book and also in the Chem 1A book, a lot of them are just one extra step, not really advanced. And so what's the equation for excess remaining? Equals what?
12 minus 71 grams of HCl.
12 grams of magnesium. Okay, minus
71 grams of HCl.
71 grams of HCl.
Multiply 5. What is it?
50.0.
50 over 100. Multiply 1 over.
Okay. And then what's next?
1 mole of HCl over 36.46 grams of HCl. Times 1 over 2. 1 mole of hydrogen over 2 mole of hydrochloric acid.
Okay, at this point I would do, it's not necessary to go to hydrogen and then magnesium. We could go straight from HCl to magnesium. Because this is 12 grams of magnesium. We need grams of magnesium here, not grams of hydrogen here.
Yeah, right.
And so we got to make sure that,
Yeah.
1 mole of magnesium, 2 mole of HCl.
Yeah, 1 mole of magnesium, 2 moles of HCl. Okay, that takes us to moles of magnesium, and then we just got to get to grams.
Yeah, that's what it's going to
And how many grams would it be?
24.31.
24.31 grams of magnesium per mole. And so everything cancels out, we'll get grams. This is the number, what do I call this second term here? If you're explaining to somebody what this second term is, what would you tell them? Okay, what would you tell them? If somebody asks you, okay, explain this equation to me, what's the first term?
Initial.
Okay, the initial amount. What's the second term? This equation. I'm sorry? Yeah, the amount consumed by the limiting reactant. That's what this is. And so how much was consumed by the limiting reactant? Got 12 grams of magnesium minus, let's calculate how many grams was consumed. The limiting reactant was 71 grams of HCl. And so we'll take 71 times 50 divided by 100 divided by 3646 divided by 2 times 2431. .83. I'm going to carry extra digits that I'm not allowed, you know. Because if I had to round this, you know, if I had to round this at this step, it would round to 12 and I'd have 0. So that's not useful for us. And so I'm going to carry some extra digits here, and then we'll let. So minus 12. In fact, I'm going to carry all the extra digits in my calculator. 0.1650 grams of magnesium. And so, you know, about 0.16 or 0.2 grams of magnesium. Let's see, we've got 2 sig figs, so let's go 0.1. Well, the precision though, so we'll just say about 0.2 grams. About 0.2 grams magnesium left over. This is a case of round off. The reason I did the calculation the way I did it yesterday, by carrying all the digits in the calculator, was to avoid round off error in the final calculations. So I don't know if you caught that, but I made a mention of carrying all the digits in the calculator to help avoid round off. Because yesterday, step 4, which we did yesterday, was how much additional HCl solution is required to react with this. And so we would take this number and then figure it out. Well, which number should I take? I should take a more precise number.
And then you do the same thing?
Yeah, you can do the same thing. You just do stoichiometry to figure out how much HCl you have. Do you want to try it?
Try it after the break.
Okay, yeah. We can take a break now. Let's take a break.